We're going to talk about the accident itself, the investigation, and then we're going to go into 11 lessons learned that I think will strike a chord with you, especially when you look back at what's happened over the past 18 months with regards to COVID, and the latest example, I think the Surfside condo failure this past week. And I think you'll see some similarities there. So the loss of the Space Shuttle Columbia was February 1st, 2003. I suspect that most of you were just babies at that time. So unless you've looked in the history books or seen videos about the Columbia mishap, it was the 113th mission of the Space Shuttle. We had previously lost the Space Shuttle in 1986, January of 86, and it was the Challenger, which basically came apart during ascent as a result of a solid rocket booster failure. But this failure was kind of really a shock to NASA and I think worldwide, because the orbiter's coming back in what normally is a benign environment during reentry. The crew's only seeing 2 Gs. We fly a series of S-turns back to Kennedy and to landing. The crew families are there ready to greet their loved ones. And the only reason it happened to be on TV was because it was the first time that we had flown an Israeli astronaut, Ilya Ramon, who was a colonel in the Israeli Air Force. So as much as we're going to look at things like, I say the widget that broke, so the foam coming off and hitting the leading edge of the wing, we're also going to talk about the organizational aspects of this accident, the decision-making modalities, the risk management or lack thereof, and other organizational issues. Here's the crew: Mike Anderson, Air Force Colonel, pilot. Rick Husband was the mission commander, Air Force test pilot. Laurel Clark was with me over in Russia. I managed the Moscow Technical Liaison Office for Space Station for 2 years, and Laurel would come over there to do dual language procedures development for the Progress cargo ship, the Soyuz capsule, the functional cargo block, and so forth. A very nice lady. Willie McCool, commander in the Navy, test pilot, Naval Academy grad, captain of the lacrosse team here at the Naval Academy. By the way, I'm in Annapolis, Maryland right now. Then Ilya Ramon, Colonel, Israeli Air Force, F-16 pilot, highly decorated. Kalpana Chawla, she was my next door neighbor when I first moved to Houston. She's a private pilot and an engineer, Ph.D. And David Brown was a Navy captain, I believe, at the time, also a test pilot. So those are the crew members that we lost during the accident. A little bit of background information. So STS-107, 113th mission of the Space Shuttle program, launched on 16 January from Kennedy Space Center. It was loaded with a double space hab module that you see down here in the cutaway drawing. It was carrying 7,500 different microgravity experiments, from biology type experiments to engineering experiments. I did put on there the fact that it didn't have a robotic arm. When we do carry the robotic arm, we're able to look externally around the vehicle. Normally we wouldn't do that, look for damage, but we could have had the arm been in place. And then back in the back of the cargo bay here, you see what's called an extended duration orbiter panel. We've got extra consumables on board because this was a 2-week science mission. A little bit of background mission-wise, we had been grounded prior to that in 2002 for about 10 months with flow liners issues, cracking flow liners for the main propulsion system, these 3 big shuttle main engines. So this was kind of an anomalous mission in that it was a science mission in the middle of trying to construct the space station. So we'll get into how that impacted decisions and sort of schedule pressure. A little bit of Space Shuttle 101. The Space Shuttle has 2 solid rocket boosters that come in 4 segments. The fuel is loaded in Utah at Thiokol and then shipped by rail to the Cape. They're assembled at the Cape. And these are what are called field joints right here. So they put these together, ensure the O-rings are fit tightly, and then they put putty over these. The orbiter main propulsion system, you've got the external tank, oxygen tank up here, liquid oxygen. This is the inter-tank area. There's a large metal beam that goes across and attaches the two solid rocket boosters. This area, the inter-tank area, is purged with nitrogen gas before launch to preclude any fires from developing in that area. Each of the solid rocket boosters produces 2.5 million pounds of thrust. And the main engines, so that's 5 million pounds of thrust. Main engines are 500,000 pounds of thrust each. So it's about a total of 6.5 billion pounds of thrust during liftoff. So the orbiter is attached to the external tank via a bipod. And you've got some flexion capability here. You've got a joint, and then over top of that joint is the left bipod and right bipod ramps, which are just spray applied foam that you would see in home building for insulation purposes. And we do that to keep ice off the tank and to keep any heating to a moderate level on this joint. And then down here are the plumbing required to get the liquid oxygen down to the main propulsion system. So here's the orbiter headed out to the pad on the crawler. You can see a little bit closer here on the upper left-hand corner. That's a bipod ramp. I'm going to show you a bipod ramp that we had Lockheed Martin build for the accident investigation. Bipod ramp came off, and so this is the projected impact site. The orbiter itself has roughly 25,000 tiles, and there's 4 or 5 different tiles and probably 4 or 5 different other ablative materials that go on the solid rocket booster and the external tank and so forth. The orbiter will see about 3,000 degrees Fahrenheit on the nose cone area during reentry and on the leading edge of the wing. So that's why we put what's called reinforced carbon-carbon panels on there, which are made from rayon fabric impregnated with a carbon epoxy compound. And I'll show you what that looks like. The the fact that it's on the side of the stack. Normally you would see capsules on the top of the stack. So it's basically flying in a debris field. So we've got to be very careful with ice forming on the pad or ice forming on the tank that could impact the tiles and so forth. When we come back from a mission, one of the largest, we have to repair the tiles. Any dings, any cracks, any damage to tiles has to be repaired. And again, 25,000 tiles on the orbiter, it's about 40,000 hours of touch labor time just to repair the tiles between missions. And missions were generally at that time about 3 months apart. So again, the bipod ramp was designed to keep ice off of it. The fact that the bipod ramp came off, looking at it numerically, was actually the 7th time that it came off. NASA was only aware of 4 times before, but the Columbia Accident Investigation Board said, we want you to go back and look at your imagery. And NASA found 2 or 3 additional times that it had come off. So if this is the 113th flight, you can do the math. Roughly 10% of the imaged missions, and sometimes we launch at night, obviously, and we don't know if big pieces of foam came off. So in the fall of 2002, we launched 2 assembly missions to the space station. STS-112 launched in October, and bipod ramp came off during ascent, just like it did in STS-107, and it came down here and hit this attach ring on the solid rocket booster, penetrated the material, the foam material sprayed on there for insulation purposes, and dented integrated electronics assembly box. So when these things come off the orbiter 2 minutes into flight, the tank stays with the orbiter until the main engines are shut off. It takes 8.5 minutes to get to orbit. These things come off at 2 minutes. They have parachutes. They're recovered downrange. They've inflation devices put around them, and we tow them back to the Cape. And that's how we found out after the booster gets back, there's an inspection done before they're disassembled and sent back to Viacol. So that was a big red flag for us. But unfortunately, It wasn't classified as an in-flight anomaly. Sort of NASA speak is IFA. It was not classified as an IFA. And that's significant because if it was classified as an IFA, the orbiter doesn't fly until we close out the mitigation effort to fix that, which would involve probably computational fluid dynamics modeling. Where else could that foam hit? Some material testing in Huntsville at Marshall Space Flight Center, et cetera. So it wasn't classified as an IFA. They told the Marshall safety people, Marshall Space Flight Center, go take a look at this study, what's happening here, and get back to us. And then we launched another mission in December. We don't know if foam came off. It was a night launch, another assembly mission, space station. And then we launched, of course, 107 in January, and big piece of foam came off again. So 2 out of the 3 flights we lost foam. And that'll be significant if when we get to what could we have done? What are the options? What could we have done to save the crew? So as I said, 81 seconds into ascent, foam comes off, bipod ramp, weighed about 1.3 pounds and hits the leading edge of the wing. The foam actually looks like it explosively pops off. And then to our physics major, the theory here was that this nitrogen gas in this intertank area was leaching through the flange and into voids, the very small voids in the foam, the imperfections in the foam. And as you ascend in altitude, you get this explosive as the nitrogen turns to a liquid, pop that foam off. That was sort of our theory. Unfortunately, going uphill, we have, and we'll talk about this a little bit later, a lot of our cameras, different camera views were not in focus. So it was difficult for the debris assessment team to initialize their models on where did this hit? Did it hit the leading edge of the wing? Did it hit under the wing? We couldn't tell, but I can tell you this, I was at NASA headquarters when this launch occurred, and there was an MPEG video about 8 hours after launch. It was being sent around via email. And the press had a copy of it. The video went to Capitol Hill. Congressmen, senators, staffers saw it. And it was sort of an, oh my God, what happened to the orbiter? Is this significant? And the way we explained it away to the press, et cetera, was that it was not a safety of flight issue. It was simply a maintenance turnaround issue. When the vehicle gets back, we'll replace the tiles, we'll patch things up, and we'll be fine. So the velocity of the foam was about 1,100 feet per second. If you know anything about like firearms, a .45 caliber bullet goes about the same speed. The foam actually slowed down and the vehicle's accelerating, the vehicle flew into it. And you can do, as a physicist, you can do the calculation there, what kind of force, doesn't matter if it's foam, 1.3 pounds at 1,100 feet per second, that could possibly do to this. And now I'll go ahead and show this. This is the reinforced carbon-carbon. It's a little difficult to see in this lighting, but there's layers of that rayon fabric impregnated with carbon epoxy compound. Takes about 2 years to make each one of the panels. So there's 22 panels on each wing. 2 years to make it because you lay on the fabric and the carbon epoxy, then you put it in a kiln and bake it, make sure there's no imperfections, and repeat that until you get this thickness. Then it's covered in a silicon carbide coating, which again, this is even, when the vehicle's in the orbiter processing facility, they kept clear plexiglass over the leading edge of the wing. They didn't want to drop a pencil or a pen on the leading edge, because if you scratch this surface, that imperfection can cause issues during reentry. Are there any questions so far? I know I've gone through a lot of stuff. Go ahead.
Just out of curiosity, a lot of these materials seem very fragile. And so why was it that those were the materials that were chosen to be put on the space shuttle and used for these launches?
Yeah, that's a good question. You know, you'd have to go back to the design trades that they made back in the 70s, you know, because the shuttle first flew in April of '81. So now you got to go back actually to the Nixon administration and look at what were we doing, right? There were a lot of different options about getting payloads into space, and the shuttle was supposed to be, at the end of the day, a truck, right? To get stuff up there to build a space station. So you've got NASA also had involved the Air Force, the military was interested in having their own military orbiter, launching it out of Vandenberg. The size of the wing is the way it is because, again, design trade, the Air Force wanted to be able to land at Vandenberg. So they needed that size of wing to do a cross, the type of landing descent approach into Vandenberg. So a lot of design trades and weight. Weight's a huge factor. The vehicle's made out of aluminum, right? So you can't, obviously, with 3,000 degrees on the leading edge, you can't have ablative material. You've got to have some type of aerodynamic structure there. And they just came up with this. This was, high tech at the time. It's not so high tech now. If you look at Dream Chaser and some other vehicles with wings, X-37 have much different materials on the leading edge of the wing. And again, that goes back to foam. We've got foam all over this tank and it's shedding. We've got big pieces of foam coming off. This is what's called acreage foam. See how thick that is? This is spray applied robotically over the length of the external tank. And during the return to flight, they were doing computational fluid dynamics. They said a piece of foam about the size of a quarter, if it came off up here in the oxygen upper tank or liquid oxygen tank, there are paths that it could take to hit the leading edge of the wing and damage the wing. So we have a very fragile vehicle. We knew that. We got a complex vehicle and it's also fragile. That answer your question? Okay, moving on. I just want to show a quick, this was a simulation of the orbiter launch. And you'll see some data up here. You've got time, elapse, height, speed, Mach number, etc. It'll give you an idea of what it looks like when the vehicle comes off the pad. And the last orbiter flight was, I think, a logistics mission to space station, STS-135. So you guys were old enough to remember those missions. So we come off the pad. One of the first things we do is roll to a heads down attitude. So the vehicle, which creates lift on the wings, is not going to fly off of the tank. Again, the solids burn for 2 minutes. Main engine's going to burn for a total of 8.5 minutes to get to orbit. You can see the bipod. These are the bipod, the ramp. The simulation makes it look like it hit near the main landing gear door area, when in reality it hit over here, panel 789. And so when you're launching to, this vehicle flew to a 28-degree inclination orbit, which when you're sitting at the Cape watching a launch, it looks like it's just launching to the east, because the Cape is at 28 degrees north latitude. Now the space station is at 51.6 degrees inclination orbit, and that's because the Russians cannot drop their boosters on China, so they have to launch to the northeast from Kazakhstan. This is a sort of fuzzy video, and I'm going to show you a much clearer one, but we didn't have this clear video. It's not that clear. After launch, we had to have actually Disney Pixar improve the video so we could try to see what happened here. Oops. It's a little tough to see because the foam comes off and hits the leading edge of the wing, and there's this debris field after it hits the wing. I'll play it one more time. Remember, this is 81 seconds in the launch, less than a minute and a half. Next one's much clearer. Bipod ramp is up here. It looks like it pops, explosively comes off, and then hits the leading edge of the wing. Remember, the vehicle's accelerating into that foam. When the Columbia Accident Board stood up, we met in Louisiana Shreveport, Barksdale Air Force Base. We did a lot of Shuttle 101 for the board. They hadn't had that training before. I got a lot of shuttle manuals and training from sim supervisors that came up from Houston. We were also aware of a lot of CNN stuff going on. And unfortunately, the program manager at the time told the press that, you know, compared the foam hitting the vehicle to a foam cooler coming out of the bed of a truck in front of you on the highway and hitting your windshield, that it couldn't damage the orbiter. But that was, I mean, you do the physics, you know, do the calculations, that simply wasn't true. I'll play this one more time. This is kind of dramatic. Okay, so best estimated impact site. Remember, there's 22 panels, 1 through 22 at the wingtip here. So we think, based on looking at these videos, that we're going to hit in this area here, probably around panel 7 or 8. If you roll this chart out, this thing is like 8 feet long, but you've got telemetry that's being transmitted from the vehicle to the mission control. You've got some roll commands here that you can see. The furthest to the west that we found any debris was the shuttle tile. I believe it was up near the canopy on the left side. And we actually called it, you know, the Littlefield tile because it was found in Littlefield, Texas, which I believe is southwest of Fort Worth. And these large debris events, debris A, I believe, is left wing comes off first, and debris BC is right wing, and then crew cabin and the cargo bay. And the debris footprint was about 240 miles long. I went into headquarters after seeing, you know, this on the on TV, and I said, geez, is there anything I can do? I get one of these to come over here. You're going to Barksdale, and on the plane with us going to Barksdale was an NTSB investigator who had been on the Lockerbie accident. He said, here's the picture of the debris field. And we got this from off of our radars, air traffic control radars. And you can see this, it's crazy. Look at that. That's a debris field. And that's just radar data. And he said, you know, Lockerbie was bad and it was difficult. I had to pick up all this stuff to determine what happened. But this is going to be crazy. So we've got sightings. We have amateur photographers and videographers from California all the way through this vehicle coming apart, taking photographs of debris events that we then stitch together to tell us a story. Okay, we've got telemetry, we've got this videography, we've got photographs. You can see telemetry going off scale high or off scale low. Some of these readings are in the main landing gear area, the tires, etc. And then we lose signal from the vehicle. But Columbia was our first orbiter. It had an extra recorder called the MADS, or some people call it the OEX. And it recorded for another, I don't know, 15, 20 seconds of data. So we get additional, and we found this. Guys are driving down the road in Texas, and it's just sticking out there on the side of the road slightly in a ditch. Found it and gave us, you know, cleaned it up and got the data off. It's like the black box on an aircraft accident. So big debris field. It was crazy when we first started the investigation at Barksdale Air Force Base. We had tactical pilotage charts, 1 to 500,000 scale. People were putting little red pins where they were finding pieces of debris. Then we got more scientific about it. You know, got computer programmers, map data, et cetera, et cetera. And we'll show you what that looks like when we get. So here's the vehicle coming in. Again, this is a simulation. These are all sensors in the left wing. Here's the main landing gear area. So all the sensors are fine. We do a de-orbit burn about an hour before we land. So we're flying a descending node to Kennedy. So we do an de-orbit burn over Western Pacific with these orbital maneuvering engines. They burn for about 3 to 4 minutes, depending on the height of your altitude of your orbit. You turn the orbiter around, so you're burning into the velocity vector to slow down, to reduce your orbit and come back for reentry. So you see bank angle, yaw, speed, Mach number, and height of the vehicle. So initially here we're at 248,000 feet. So it flies a series of S-turns, and to control the vehicle, because there's no atmosphere at this altitude, we've got reaction control system, jets in the nose and the tail, but during reentry, we just use these to control the vehicle. So you'll see the California coast coming up here pretty quickly. I actually had a video of the crew that they took on the flight deck during reentry. That was the cassette was found by the folks that did the debris search.
Adam, do you want to go ahead and ask your question right now?
Go ahead. This plays for another minute.
Yeah, sure. So I was wondering if there was the debris field you were talking about earlier. Did it cause any like structural damage or injury on the ground?
Now, we got extremely lucky. You know, we lost 2 more people as a result of this accident, but they were, I forget what agency they were with, but it was a helicopter crew assisting with the debris recovery effort. So 7 astronauts died and 2 helicopter crew members died. If you think about, you know, loss of life, no one on the ground. So this is 9 o'clock in the morning in Texas. Some of these small towns, one in fact had a chemical plant nearby. And when you listen to the residents talk about what they heard before they even saw anything, they said it sounded like a freight train, and then like almost like an explosion. They thought the chemical plant had blown up, but nobody on the ground got killed, which is just amazing. Partly because it's, you know, it's Saturday morning, not a lot of people are out, and the fact that it hit in primarily rural areas. So this annotates when we got debris coming off. So this wing is breached. So we've got hot plasma coming inside the wing. This is all aluminum structure. There's other, you know, materials in here with the RCC, and the investigation, you know, during some assessment, we've got metal slag up here, we've got aluminum slag up here in this ohms pond. So we've breached the wing, hot plasma, sensors are going offline. Sensors are anomalous high or anomalous low. Did the crew know this was going on? I did, doing a little bit of research. One of the flight controllers that has given a brief on this said that the control stick was grabbed at the last second by the mission commander, and that I think some APU switches were touched. This is a very benign environment. You're coming in at 2G. I mean, you see more G than that if you're on, you know, a ride at the county fair. One of the first things we did when we got to Houston was to put every member of the Columbia Accident Investigation Board into the simulator so they could see what it would look like. Okay, here the RCS jets fire. We're going into a left wing down attitude. Mach 20, 218,000 feet coming over Texas. And what you'll see at the very end of the video, because you've got this aerodynamic drag on the left wing here, so it's trying to pull the orbiter down. And you'll see, you won't see it here, but there's aileron trim that tries to correct that. And then these jets try to keep the nose of the orbiter up at the last second before it departs controlled flight. So this wing has been destroyed. Left wing comes off first, right wing, and then the main body. We're coming up on this.
Holden, do you want to go ahead with your question?
Yeah, go ahead.
Yeah, I was just wondering, I'm not even sure if it's kind of possible for this to happen, but was there no mechanism for them to separate the inhabited portion of the shuttle from the damaged portions?
The first, I forget, 2 or more shuttle flights were just, here the jets all firing. The first 2 or more shuttle flights where you just had in the left seat the mission commander and the pilot in the right seat, they had ejection seats. And then okay, we consider this vehicle operational. We don't look at escape pods. Maybe we did. I don't, I wasn't around back then, obviously. We did look at escape pods in the 1995-6 timeframe. Boeing was looking at what could we do, because you've got some aircraft like the F-111, which was a fighter bomber and also electronic warfare aircraft. It didn't have an individual ejection seats. It had a pod. Pilot and bombardier navigator came out at the same time. So they looked at that. And I think the decision came down to, would we induce more risk into the system overall if we put this escape pod in here? See, you've got 4 crew members on the flight deck, and then TBD, usually 3 or 4 on the mid deck, and there's lockers down there, your kitchen, your toilets down there, et cetera. How do you get that volume out of the vehicle safely? And if we talk about, options, what could we have done on orbit? If you could get the vehicle to a safe altitude to be able to bail out, the bailout pole was added after Challenger. So the engineering decisions that led up to not really having a robust escape system, they were there. Look at the capsules, the Dragon CST-100 by Boeing, which is supposed to fly this month in July, have robust launch abort systems to take the vehicle, even if it's on the pad, to take it off the pad and safely land the crew, but not on the orbiter. Did that answer your question?
It does, yeah, thank you.
Okay. So here's what it looked like. These were TV cameras over Fort Worth. And so in the flight control room, they've lost contact with the orbiter, and this appears on TV. And the flight director says, lock the doors, preserve your data, and away we start on an investigation. In bottom right-hand corner is infrared video from an AH-64 Apache helicopter that just happened to be on a training mission that morning in Texas. And they saw this, this streak fly across the sky. I said, let's get that on video. So the heaviest mass items are here leading this pack of debris. So the engine, shuttle main engine turbo machinery, it lands in Fort Polk, Louisiana. So we got debris from Fort Worth down to Fort Polk, Louisiana. So we had a
Dr. Kinghorn?
Go ahead.
Dr. Kinghorn had a question in the chat if you wanted to ask.
I'm okay.
Could we have Brian's question followed by Othello's question, because they're kind of linked?
Okay.
So yeah, my question, actually, I was going to wait, but my question was the end of that simulation you showed was at little over 200,000 feet, which is quite a bit higher than an airplane goes. At what elevation was the actual point where the shuttle started breaking apart?
It's left wing, right wing, and I don't have all the data there, so I can't answer that totally accurately, but the crew compartment came apart at about 150,000 feet.
Okay.
And, there's a lot of sensitivity to picking up crew remains. The astronauts were responsible for that, but I will say that early on, we weren't scientific about it. Later, we sharpened our pencils and said, okay, if the vehicle came apart here, say between 160, 150, it's going Mach 15, what's the ballistic coefficient of a crew member in a flight suit with a helmet on? So after we did those calculations, it was, within a day or so, we found all the crew members, which was good. So we had a contingency. Was there another question? I'm sorry.
Yeah, I had
Yeah,
one.
Othello.
Where was the final impact located at?
Well, it's this debris field. It's there's a center line. The vehicle's flying this path to Kennedy Space Center, right? So along that path, there's debris, and 2 to 4 miles either side of that center line of that trajectory drawn over the ground, you've got debris. And I'll show a chart here in a second about the recovery effort, which was just absolutely amazing. So it's not one place, it's all over. In fact, the state of Texas put in their fishing licenses and hunting licenses. I don't know if they still do this, but they did in 2003, 4, probably longer than that. If you find something that looks like a, a debris, which would be from Columbia, please notify, and they give a NASA phone number. I believe that we'll be finding pieces of debris in Texas, and for years, because it was all over the place. A lot of it was, very small pieces, but I'll show you how we reconstructed it, and some of it was pretty big pieces. Did that answer the question?
Perfect, thank you.
Okay. So the board, there was a mishap plan for the shuttle. There's a mishap plan for space station, right? So space station first element goes up in 1998. Now it's 5 years later. We have these 2 plans, but we also have an integrated plan between shuttle and station, specifically for an accident investigation board. 1986, the president appoints former Secretary of State Rogers. We have the Rogers Commission. We wanted to get ahead of the power curve, I think, in writing this integrated plan. So we had a list of people already named to be on the accident board. And these were the commander of the Air Force Safety Command, commander of the Navy Safety Command. MIT had a member. There was ex officio member was the NASA Safety Mission Assurance person, and on and on. We gave them some limited training. They would attend mission management team meetings, simulations, but mainly for launch, where we thought, here's the highest risk phase of flight. We never did it for reentry scenarios. So I think they weren't as well trained as we wanted them to be. One person on the board was not named, and that was the chair, and they selected Hal Gehman. And here's some of his data, retired in 2000. He started out as a Swift boat, which is a armed patrol boat skipper in Vietnam, Mekong Delta. We used to call it the Brown Water Navy. So he's a tough guy. He's been around. Then he's NATO Supreme Allied Commander, Commander Joint Forces Command. Just a wonderful career, 4 stars. He led the investigation into, I'll call it the organizational accident and the terror bombing of DDG-67, which was the USS Cole. In that case, it was a lot more than just, the terrorists putting charges next to a ship. That the Cole should ever have been in the Yemen harbor. Some lieutenant commander in the Persian Gulf said, we need the Cole here at this date and time, no exceptions. So the Cole had to steam at 30 some knots versus conserving fuel at 20 knots, and there you go. You get a vehicle in a bad guy port. So he knew about the organizational aspects, the risk management, decision making, and so on. And I think that was really his sweet spot. He was also on the Iowa USS Iowa investigation, where we blew up a turret and killed about 15 sailors. And about 2 weeks into the CAIB investigation, I said, does anything bother you about this? He said, yeah, Dave. He says, getting it wrong. He said, we got it wrong on the Iowa investigation. We blamed a poor sailor for that turret blowing up, and it wasn't him. It was a design flaw in the powder, et cetera, et cetera. So he said, and also, if you look at the Concorde accident, the first investigation report that came out from the Concorde that crashed in Paris ended the entire Concorde flight program for the French and the British. They got the investigation wrong. So he said, Dave, getting it wrong, and I'm going to make sure we don't get it wrong. So he was a pretty incredible person. A Penn State graduate. He was either industrial engineering or a physics degree. I can't remember. So field recovery operations, we got stuff everywhere. We got people calling NASA. We set up phone banks at Johnson Space Center. Got forest fighters. The only good thing about this with regard to forest fighters, Forest Service firefighters, was the fact that it wasn't a big, busy time of year. Let's say, there's not a lot of fires burning in California or Arizona, so we had them pretty much full time. So they walked 20 feet apart. We covered 1,062 square miles. We stopped in April because we stopped really finding stuff, and plants and stuff were growing up. It was harder to find materials. But these guys had GPS, they had cameras, so they would geolocate a piece of debris, take a photograph of it, bag it in plastic. There was some hazardous materials out there, and then it was transshipped to different places in Texas, and then ended up at the Cape. We found basically 40% of the dry weight of the vehicle, which is incredible. And the operation cost us about $300 million to keep these guys motivated, because they would walk 8 to 10 miles a day. We set up camps, you know, where they could wash their clothes, dry their boots out, get a good meal, get a good night's rest in a cot, etc. This is typical of any accident investigation. I've seen this in the military, the Marine Corps. They bring your jet parts back into the hangar, and we go through the debris to try to figure out what happened. In this case, you got a lot of stuff, right? 87,000 parts. Back here, we'll take a look at this in the next chart. We reassembled the wing, RCC panels, but you can see here, we're trying to locate tile on the wing. Each one is numbered, so we can do that. There's a nose gear door and nose gear and so forth, just laid out in this hangar. And then the crew hardware and gear was locked over here in a small area. This is the Administrator Sean O'Keefe taking a look at our reconstruction of the leading edge of the wing. This really told us a lot about what happened. We kind of suspected it going in, but this really proved that, you know, this is the area that we really need to concentrate on. And then we conducted some tests. These were conducted at the Southwest Research Institute, San Antonio. We use an air cannon. Typically, these air cannons were used to shoot chickens at plexiglass cockpits to tell whether or not we'd get damaged by hitting a bird in flight, going 250 knots versus 300 knots, et cetera. So these are the RCC panels. These are called T-seals. They're in between each panel. These panels came from the shuttle Enterprise, Orbiter Enterprise, which was displayed on the Intrepid in New York City, because we didn't obviously want to do destructive testing on panels that take 2 years to build from the orbiter fleet. So the foam is going to come left to right, and you'll see what it does to the RCC. There were a lot of NASA people saying at this time, foam couldn't have done it. Foam could not have done this, not at all. There's no way. The RCC is tough. So we got some big pieces that go back into the wing. It's kind of dramatic, so I'll just show it to you one more time. This is the inside of the wing, and in here, for you people that want to go into engineering field, mechanical engineering in particular, these are strain gauges to see the force, foot-pounds of force. This is the inside of the wing. This is the RCC panel inside. I believe it was on flight day 2, the orbiter did a 90-degree maneuver. I think it was to the left, so just basically a 90-degree yaw maneuver with the jets. And we had radar data. I forget, one of the services had some radar looking at the orbiter as it flew over. And something departed that had a radar signature, departed the orbiter after doing this. So we were kind of theorizing that it was a large piece of RCC that had been blown back into the interior of the wing, and then the maneuver allowed it to come out and float away from the orbiter. This is Scott Hubbard. He was our one NASA person on the board. Scott was the Center Director at Ames Research Center, and he's just taking a look inside the leading edge of the wing. So you get a sense of scale on how big those panels were, and how big the hole that the foam made. So the report was delivered 28 August. Remember, the accident's 1 February. I remember, I think it was the March timeframe, we sat down with the NTSB sort of advisors that were with investigation, and some Navy folks, some Air Force folks, on how to write the report. I thought it was kind of interesting how NTSB does it. They do field reports, and they're rolled up into a docket, into this final technical report, et cetera. And Admiral Gehman said, absolutely not. After we sat there for 4 hours, he said, I want this to be a narrative report. I want it to read like a novel, something that you take to the beach and you go to page 12 and you go, oh, no, they're not going to do that. Go to page 13. Oh my God, they did that. And give some history on human spaceflight at the same time. So that's, if you ever have a chance, take a look at this. I've got a link in the back on the Columbia report. It's really, and we also hired some professional editors. Leading aerospace author was our editor. So in this photo, Admiral Gehman gives the report to Administrator O'Keefe. It also went to the White House and Capitol Hill, lots of hearings. I've got links to hearings in the back, et cetera. So the focus was on systemic, cultural, organizational issues, decision-making, risk management. And I think there were a total of 29 findings, recommendations, 15 of which were classified as return to flight. In other words, thou shalt do these before you launch another orbiter. And these are the lessons we'll go over. How am I doing on time, Brian? I'm not looking at a clock here.
You're about 9 o'clock now, so you're doing okay. There was a couple questions. This might be a good time to pause. Mateo, you want to call on them?
You have Othello again, and that was the only other question that I saw.
Oh, there's one was, what does RCC stand for, from Vivian?
Oh, it's called reinforced carbon-carbon.
Okay.
This is called a coupon. This is an RCC coupon. This was provided. Admiral Gehman added a Nobel Prize winning physicist like they had on the Challenger accident. He took this back to Stanford and was doing some testing on it. So that's sort of NASA jargon, RCC, for the leading edge and the nose cone.
And then my question was, how did you manage to identify like each different parts that you would find from the debris, and especially like the smaller ones? How are you guys identifying where those went and what they were to?
Well, we had all the Kennedy experts, and those guys are, they touch the vehicle all the time, right? So they bring, some of the big stuff is easy. You've got a piece of the canopy system. You've got tanks from the orbital maneuvering engines. Main landing gear, tires, all that stuff, really easy to identify it. Then there were big barrels of really small pieces that we'll probably never know exactly where it came from on the vehicle, but pieces of tile, they're numbered. So you've got vehicle experts that say, okay, that's this, because they've touched the vehicle during the orbiter processing periods and maintenance periods, et cetera. So they know what they're looking at. But again, back to the most important part, the slag material that we found on the OMS pod, reconstructing the leading edge of the wing, and so forth, were real truth tellers for us. So I'm gonna try, I'm not sure I'm gonna get through all 11 of these. You'll have the charts to take a look at them, but I suggest that you think about these when you get into an organization, out of the academic world into an engineering organization, science. This could apply to a lot of different organizations, even non-engineering organizations, in terms of the issues that we're going to talk about. So the program manager, this deals with lack of adequate independent engineering and safety authority. The program manager was like a king or a queen. I mean, they held tremendous power vis-a-vis your safety and your chief engineer. So we were basically out of balance. And the board looked at a lot of different organizations, Navy, Air Force, DuPont safety system. One of the things that they borrowed from the Navy was this concept of independent technical authority to bring back that check and balance. So the engineer, your chief engineer, your chief safety officer, in the case of human spaceflight, you also have a chief medical officer. They have authority now. The program manager cannot tell them we're going to waive that requirement. So it was less advisory and more authority. And that was very important. Ignoring early warning signs of pending disasters. Same thing can be said, I think, based on what I've read about this, this condo that came down, the concrete spalling, the cracks, et cetera. inspections that were done in 2018 that we didn't do any maintenance on, et cetera. The shuttle was the same thing. Our system level requirements were foam doesn't come off the vehicle. It flies in a debris-free field. That was never true. We had foam coming off on every mission and impacting tile and having to repair it. But what we did over time was to normalize it, right? So if you've got a scatter plot, time versus some metric, right? And I try to fit a line in there, a curve, straight line, whatever. And I look at trends and I go, okay, within 1 or 2 standard deviations of this line or curve, you know, I think we're okay. Maybe I have some outliers, but we've normalized it in the fact that we got away with it. We were maybe not safe, but we landed safely, and it's not a safety of flight issue. So we ignored these things. We did the same thing during Challenger accident with started with scorching of O-ring, the primary O-ring, and then scorching of the secondary O-ring. Then we have burn through. So what NASA has some particular interesting language when you think about the scatter diagram. Oh, it's in family. We've seen this before. It's not a safety of flight issues. It's an acceptable risk. So we're going to continue to fly. So we've ignored those warning signs, both in Challenger and with, especially with big pieces of foam coming off the orbiter. Lack of full understanding of the vehicle. Like I said before, we consider this an operational vehicle, 4 flights into the program. It's just a big truck. We're going to go build a space station. So we fly out of these missions, mission 25, we lose an orbiter. And we get cranked up on our safety and systems engineering and integration. And we fly safely throughout the 90s. We get into the 90s, we start cutting the budget. We have less money for test and evaluation, especially for those outliers, right? I want to go do some CFD modeling. I want to do some wind tunnel testing. I want to do some material testing. We didn't have the money to do that. So again, we go back to we're dispositioning in-flight anomalies as in family and not resolving the issues through hardware testing. We probably had over somewhere around 300 different analytical models, right? So we're depending on these models to tell us a story. And some of these models are not representing what the hardware is actually doing. And then over time, as the system ages, we started to accept these things. We had sort of this attitude of lack of engineering curiosity and rigor. We get lazy, if you could use that term. And we lacked a full understanding of the space shuttle system. It's kind of like a Faustian bargain, right? You build this very complex, very delicate space system. It's your responsibility to maintain it at the safest level possible, but we weren't doing that. Less than adequate systems engineering. One of the things that the Columbia board found, we had 80 people in the systems engineering and integration office. During return to flight, we find out that only a handful have ever even been in the academic background of systems engineering. Not that they weren't good engineers, but systems engineering integration, we typically say there's 8 technical processes, 8 technical management processes. One of those technical management processes, continuous risk management, and the shuttle program was grandfathered in. They didn't have to do this. What CRM does is continually identify risks, and for the high risk, we'll develop mitigation plans and see how they track to reduce the likelihood of that risk occurring. And a risk is to your requirements, to safety requirements, to technical performance requirements, and so forth. So they got grandfathered in. They didn't have to do it. We had less than adequate systems engineering, and one of the fixes was went back to fixing this organization, putting new leadership in place and implementing continuous risk management. Less than adequate quantitative risk assessment. That we talked about, this debris assessment team. They've got an Excel-based model that's based on ice coming off of the tank or the launch system, the towers, and hitting foam. Can you imagine that? It's ice hitting foam, and it's not foam hitting RCC. So we start off with the wrong model. Now the team members of this team, when they debriefed out, said that, hey, we don't see any safety of flight issue. However, we've got all these issues with regard to the uncertainty of this model, but we didn't do anything. And if you talk about what could have been done, we probably needed to know by flight day 7 that we did have damage. And there's some different ways we could have done that with Air Force assets or National Reconnaissance assets, or even doing an EVA spacewalk to get an astronaut's head below the leading edge of the wing to see what's happening down there. We didn't have a dissenting opinion process. So we have these weak signals, a lot of engineers, emails flying around the organization. Hey, we need to get some better imagery. We need to get some spy satellite imagery. And this was shot down on multiple occasions, including all the way to the headquarters level. So these dissenting opinions that are out there, alternative technical views, if you want to call them that, I think you need to welcome those as a manager, have that discussion, have that critical conversation about what are we doing? Is it a safety flight issue? We never got there in this mission. So former Administrator Mike Griffin said he put in place a system in order to make a really bad decision. You have to have a double fault. In other words, you have to fail on the engineering or functional side, and you also have to fail on the programmatic side before you can make a really bad decision. And we've actually codified this. This is in NASA procedure requirements documents. We have this dissenting opinion process. Less than adequate safety program. Sally Ride, I think a lot of you probably remember that name. She was also on the Rogers Commission, first female astronaut at NASA. During one of our public hearings, she said, I hear echoes of Challenger, because it's the same. There was, as Admiral Gehman said it, there's no there in the safety program. He kind of called it the silent safety program. So you've got safety managers and representatives at the mission evaluation room, mission management team meetings, sitting there either concurring with decisions or not making any comments at all. So there was sort of a lack of rigor. Safety people need to be trained, properly resourced, and have the appropriate authority, which goes back to independent technical authority. You can never burn a risk down to zero. I think you all probably agree with that. You know, we tried to burn it down. Use that term burn down, that just means to mitigate the risk. We saw that in the COVID epidemic. We could do things like stay home to reduce risk. We can wear masks, we can do all kinds of stuff, but you never get it down to zero. So you've got to accept some level of residual risk. And for us, we blocked communications. We missed opportunities to identify, classify, develop any mitigation strategy in real time to deal with this risk of the debris strike. What we needed to get down to was, is this a safety of flight issue? And if so, let's go do our, redux of Apollo 13 and see if we can save this crew. So the recommendation here is to, risk management training, decision analysis training, and so forth. Making decisions in an engineering organization may be a little bit different than others, but we look at cost, schedule, technical performance, and safety. So those are your decision attributes. How you want to rank those or rate those, I want to put 50% on schedule. That means that you're biasing your decision towards schedule issues with regards to that decision. I think that's where we were. We were schedule pressured to get this mission in the rearview mirror. And so we downplayed the significance of safety and technical performance. And I'll show you a chart here in a second. It comes from our continuous risk management process, where we score a risk on likelihood and consequence. We could do it quantitatively, we can do it qualitatively or linguistically. But this risk was very high. This was not a low risk. And the consequence was very high, and we didn't get that. And we clearly, had some issues with regards to attribute rating. This came from the Constellation program, which is our return to the moon. It was actually borrowed from the Space Shuttle program. And so we use a logarithmic scale for likelihood or a linguistic scale. If you've got the data, you use your logarithmic scale. So we were probably thinking that this risk is 1 in 100, right? So if we were even doing continuous risk management, we would have scored it here for likelihood. And for consequence, it would have been a 1, because so over here, minor damage or non-essential flight to non-essential flight assets. The risk is actually over here. It was 1 in 10, which is very high, and catastrophic damage, loss of vehicle, loss of crew. We weren't doing this process before the accident. We did it afterwards. poorly defined roles and responsibilities. Part of what we did in our risk management rubric was to capture lessons learned on our risks. So, you know, how do we identify it? How do we mitigate it? What worked, what didn't work? One of the things we find when we look at programs that have issues or failures, classically, two things always show up. One is poorly defined roles and responsibilities, and the other is less than adequate communication. So poorly defined roles and responsibilities in this case relates mainly to the communications paths that were shut down. People on the debris assessment team said, well, how do I get this imagery? Who do I even report this data to? How do I get my message up to you? So that was an issue. Differing risk acceptance attitudes. I like to think that your risk acceptance attitude is like your fingerprint or thumbprint. It's everybody's different, right? You can, some people like to take risks. They like to jump out of airplanes. Some people, you know, drive cars for NASCAR. Some people are risk averse. Some people are sort of risk neutral. Some people are risk takers, right? And it has to do with your knowledge and background, individual biases and heuristics that you might use with regards to decision-making and acceptance of risk. So there was a big difference between management on the space shuttle program and the engineers in the bowels of the program working the issues, right? So we had this difference in attitudes. I think, you know, the recommendation in my mind was, hey, let's do some training and simulation. We beefed up the mission management team with this type of training to listen to weak signals, to identify what's your attitude with regards to this risk. Are we risk averse? We risk accepting, you know, where are we? Can we normalize that through this conversation? One of the things I did for my dissertation was to interview 2 NASA administrators, 2 shuttle program managers, and other managers in the shuttle program. And I said, on a subjective scale, where were you? 0 to 10. 0 would be, I'm so risk averse, I would park the orbiter in a museum and not ever fly it again. And trust me, there were NASA managers that said, this vehicle is too dangerous. We lost 14 astronauts over 17 years. We shouldn't fly it anymore. Let's go build something else, put a capsule on top of the rocket, not fly this thing in a debris field. It's just too complex. So what we got out of this cumulative distribution function was, before the accident, the mean was 6.3. So it's this blue curve over here. And I think that's where you need to be if you're in sort of a, if you're working with risky technology, et cetera, maybe even further to right, who knows? I mean, you're going to hear a lecture tomorrow about drugs and formulating, you know, things to keep people healthy. Where do you want to be on that curve? And then after the accident, we were down here with a mean of 2. Over time, during the return to flight process, it creeped back here. And I think you need to be here in a risk acceptance modality if you're working with things that are, you know, technically challenging. So we looked at these 11 lessons learned. We looked at risk. We looked at decision making and organizational framework. So I'd just challenge you to keep these in mind when you go to an organization. I think you're going to see them. I think we see them every day, actually. And so thanks for your time and attention. One item here: 28 months after we launched Columbia was STS-114, a return to flight mission. They went and demonstrated some shuttle tile and RCC repair techniques. But guess what happened? During ascent, we kept those protuberance airload ramps, which were next to that oxygen feed line that goes down the side of the tank. And there's also some cable trays there. And the thought in the design was that we put these airload ramps on there and they keep the air from being too turbulent and vibrations on the feed line and trays. So we lose a big piece of foam during STS-114. The administrator was very unhappy and grounded the fleet for a year. So 28 months to return to flight, fly shuttle mission, lose a big piece of foam in a different area, ground the fleet for a year. But we went on, after that, we flew 12 construction flights, multiple logistics flights to ISS. We built that vehicle and still using it today.